Good morning, one and all. Here we are going to talk about expectation of a random variable x. Random variables are functions that assign a probability to some outcomes in the sample space. They are very useful in the analysis of a real-life random experiment, which become the complex from a simple sample space as input and assign some real numbers to it. The expectation is an important part of random variable analysis. Now let us see about the random variable of a continuous random variable and discrete random variable. First let us see about the expectation of discrete random variable x, which takes the value of x in a particular interval for the values a1, a2, etc. an with probability mass function as the number, where e of x is equal to summation over x into p of x, where the p of x is the probability of the given random variable x. Then the expectation of the continuous random variable, which takes over as the probability density function f is the number e of x, which is taken integral over minus infinity to plus infinity into x into f of x dx. Let us see about the change of variable formula. That is, let x be a random variable and g is a function. It comes from r to r. In this also we are taking the two cases, when x is discrete and when x is continuous. Here also for the values a1, a2, etc. up to an, we can make it as a function. So e of x will become e of g of x, where the summation over g of ai into p of x equal to ai. In the case of continuous, e of g of x is equal to integral over g of x into f of x dx. These are all the expectations definitions for the random variables in the case discrete and continuous. Next let us see about the variance. The variance of x is a random variable. It is also a number, where we denote the variance of x is equal to, in terms of expectation, as e of x is equal to, variance of x is equal to e of x minus e of x the whole square. We can also give an alternate expression for this variance. For any random variable, variance of x, e of x squared minus e of x the whole square. Then the expectation and variance under the change of units for any random variable x and for any real number r and s, we can denote e of rx plus s as r into e of x plus s. In that same case, variance of r of rx plus s is also denoted as r squared into variance of x. Next, let us see about the rules of the expected value. What are all the rules in expectation is, number one is e of ax plus b. Here a and b are two constants. Then in this, a into x plus b is a simple constant. Then we are taking the expectation for these two values as, first let us, e of ax is denoted as a into e of x, because a is a constant, so e of a will become a, just a into e of x. Then x is a random variable, plus the second quantity e of b is also noted as b, where b is a constant. This is one proportion for the expected value. Then the properties of expected values are, number one, the summation property is, for any two random variable x comma y, e of x plus y, which is equal to e of x plus e of y. Here we are providing the expected values for x and y. Then if x and y are independent random variables, in that case the e of xy will become e of x into e of y. In general also we are able to write the same rule, e of xy equal to e of x into e of y, but in specified cases we can note it as x and y are independent random variables. Then another one property is if x is a random variable and a and b are constants, then the variance of ax plus b is denoted as a squared into v of x. Next, let us see about the moment generating functions. In that case, we are able to know about the previous results, mathematical expectation. In that case, we are see in discrete case, p of x is equal to x. The mathematical expectation is nothing but the arithmetic mean or simple average or mean. So, e of x is equal to just sigma x into p of x or sigma xi into pi, where I denotes from 1 to n. Then the mathematical expectation is the sum of the products of the different possible values of the random variable and the corresponding probabilities. If x is a continuous and continuous random variable with probability density function f of x, then e of x is denoted as integral over minus infinity to infinity x into f of x dx. In p of x, just we are noted as probability function. If it is in the case of continuous function, the function will become probability density function. Next one is moment generating function. This is denoted as mx of t or simply m of t. M of t is called the moment generating function for any random variable and can be used to derive any non-central moments of the given random variable, and it is also exists in the neighborhood around the value t equal to 0. This moment generating function is useful in determining the distributions of functions of the random variables. In next class we see about the distributions, naming distributions like binomial, Poisson and normal distributions. In that cases we are able to derive the moment generating function for all the given distributions. The moment generating function for any random variable is denoted as mx of t, and it is defined as mx of t is equal to e of e power tx, where it taken from summation x is equal to I to n 1 to n p of x, x into p of x is equal to x in case of discrete random variable. In the case of continuous random variable, we are able to take it as x into e power tx f of x dx. Then the integral is absolutely convergent integral in the case of continuous random variable. Next, a random variable x may have no moments, although the moment generating function exists. In that case, there is no moment, that is mu1, mu2, mu3 up to mu n, there is no moment, but we exist moment generating function. In the case when a random variable x can have moment generating function for all moments or some of the moments, yet the moment generating function does not generate the moments. And then in third case, a random variable x can have all or some moments, but MGF does not exist except perhaps at one point. In one point only we are able to get the moment generating function. In that case we are able to derive all the moments for the given random variable. Then the moment generating function is the sum of independent random variables is equal to the product of their MGFs. This one property having the moment generating function, that is the sum of the independent number of random variables means m x1 plus x2 plus etc. up to xn of t is equal to product of their respective MGF, that is mx1 of t into mx2 of t into etc. up to mxn of t. In that case also we are able to provide it as a probability function, that is m Pn, which is where I is equal to 1 to n, xi of t is equal to product of m xi of t. These are all the definitions and properties of MGF. Then the moment generating function also has the property that in the case of expected value, that is mx of t equal to e of e power tx, where t is an open interval that contains 0. In that case, MGF at t equal to 0 How can they prove this property as mx of 0 which is equal to 1? In the case mx of t, we are having the formula as e of e power tx. We have to substitute t as 0. Therefore, we will get e of e power t into 0 into x. E power 0 is 1. Therefore, we have e of 1 is equal to 1. Then, moment generating functions are the powerful tools. In that case, we are having some properties, that is mxy of t equal to e of e power ty. Then my of t is equal to e of t power alpha x plus beta. Then my of t e of e power tx plus t beta. Then my of t, in that case we are able to write it as in product rule, e of e power t alpha x into e power t beta. These are all the properties for MGF. Then the moment generating functions, which are powerful tool in probability theory to use, analyze and random variables. They are also able to transform the given random variable into a function. That is, they simplifies the calculation of important characteristics such as mean, variance, skewness and kurtosis. These four important characteristics play the very crucial role in our MGF. Then the moments are quantitative measures. They describe the shape and characteristic of a probability distribution. The four characteristics: first moment is called as mean, the second moment is called as variance, then the third moment is called as skewness, and the fourth moment is named as kurtosis. These are all the four moments. They are able to qualitative the measure, then they able to shape and give the characteristics of the probability distribution. In normal distribution, we are getting the shape as bell-shaped curve. Then here is a property for the MGF. In this, we are having a neighborhood property. That is, if MGF exists in a neighborhood at t equal to 0, then all the moments of x exist. Here we are having the simple proof for this property. That is, from the definition of mx of t, e of e power tx, then we have to substitute the e power tx value as t power x power n by n factorial. Then we will get t power n by into x power n by n factorial. Hence, all the moments exist in this neighborhood. Then we are having the next property as uniqueness property. That is, the MGF is unique for all the given random variables. If two random variables have the same moment generating function in a neighborhood of t equal to 0, then they have the same distribution. That is, two MGF, but they are having the same distribution. Next, this uniqueness property determines the sequence of moments. Since the moment sequence uniquely determines the distribution under regular conditions, they equal the moment generating functions, give the identical distributions. They are having the same distributions. Next property is known as characteristic function. Here also we are having the MGF of a linear transformation. In this property, we are having if x is equal to y equal to ax plus b, then we are getting the same value as my of t equal to e power bt into mx of t. Then my of t equal to e of e power t. Then mx of at will be written as ax plus b. Then we will have as e power bt into e of e power atx. Here e of e power atx is nothing but our moment generating function. Hence we get mx of at and my of t, which is equal to e power bx into mx of at. Then next property is the sum of the distributions, that is sum of independent random variables. If x and y are two independent random variables, then we will have mxy of t equal to mx of t into my of t. Here also we are having the additive property, that is mx plus y of t equal to e of e power tx that is x plus y, then we will split it as e of e power tx into e of e power ty. Here x and y are two independent random variables, then we will have that e of x plus y அல்லது m of x y plus my of t equal to mx of t into my of t. Then this property determines the distribution type, that is moment generating function can also describe the distribution type. In this we are having the uniqueness property that determines the sequence of moments. Then the MGF can also used to identify the distribution of the given random variable. Next one is characteristic function. In this also we are having any random variable x, it may be discrete or continuous. Hence we are having the definition for the characteristic function is pi x of t is the notation for the characteristic function. Then we are able to describe the pi x of t in terms of expectation, that is e of e power itx, where t belongs to r. Then the characteristic function exists for all the random variables and for all the values of real number t. If two random variables have the same characteristic function for all real t, then they have the same distribution and the characteristic function is uniformly continuous in R. Thank you all. In next class we are having the distributions.